The famous Italian monk Giordano Bruno in 1586 published a book in which he said the sun is a star and that the earth was a planet and that other stars certainly had planetary systems and probably even had life. And for that and other radical things that he said, the church burned him publicly. You could say that extrasolar planets was a much hotter field back then.
Exoplanets were almost as silly as looking for extraterrestrials, little green men on other planets.
Seriously, looking for planets was a kind of weird topic.
The whole field had sort of a snake oil sheen about it because over the previous 50 years or so, there have been many, many claims of the first extrasolar planet ever. And the one thing all those claims had in common was that they were wrong.
In San Francisco, California, astronomers Jeff Marcy and Paul Butler were quietly looking for Doppler shifts, changes in the observed color of light from the star.
I literally spent the first 8 years of the program simply trying to improve the techniques involved in making these sort of measurements, mostly totally under the radar. Nobody knew what we were doing and nobody cared.
A ray of hope that it might be possible to detect a planet came with the discovery by Dave Latham and Zvi Mazet of a mysterious object orbiting the star HD 114762.
They announced the detection of an object that they called a brown dwarf. They looked and they didn't see it in a telescope, so if it was a star, if it was 1,000 times the mass of Jupiter, they would have seen it.
To this day, it is not known whether this object is a planet, a brown dwarf, or even a low-mass star, but its discovery emboldened others to continue the search. A different and dangerous approach to planet hunting was underway in Canada. The team of Gordon Walker and Bruce Campbell employed the deadly gas hydrogen fluoride in an attempt to precisely measure Doppler shifts.
And he showed me their setup in Canada at one point. One person would be in there doing the setup, and the other person would be outside of the room looking through a porthole with 2 gas masks. And his job was, if something went wrong, throw on a gas mask, run into the room, throw the gas mask on the other guy, and drag him the hell out. Any good science should have an element of danger. There should always be at least the vague hint of death involved. Otherwise, you're not really on the cutting edge. They really pioneered the whole field, just a spectacular achievement.
We're all here because of the work that they did.
In 1992, another incredible discovery piqued the interest of astronomers looking for exoplanets. But these new exoplanets were not orbiting a regular star. They were orbiting a pulsar.
2 very small bodies got detected at Arecibo by Wolsham and his colleagues, and they really got us scratching our heads. So we call them pulsar planets.
Wolsham and Frail is somewhat of a special case because I don't think anyone really doubted that these were planets as much at the time, but they were planets around a bizarre object, a pulsar.
But they really were the first 2 bodies to orbit a dead star, not a currently shining star.
The formation of planets is an incredibly robust process. And that's what that discovery told us, and we missed it because we didn't understand it.
We should have understood that planets don't come in ones, that they come in systems. But we were still focused on finding the very first planet.
Halfway around the world in Geneva, a pair of Swiss astronomers were hard at work developing a different technique. Their instrument relied on fiber optic technology, and they used it to turn their eyes on exoplanets.
My first day of work, I got this booklet from Michel that was the ultimate knowledge of data processing of spectroscopy. There was almost nothing at that time, and that's it. And we had to to do this instrument. And we designed this practically without much support from anybody else because the other people felt that this was not interesting.
After a few months, already at the end of '94, we got a signal of variability for several stars, not only one, several stars.
We realized very rapidly that the instrument could be far more precise than we thought. So I started with a couple of stars a bit more intensively, and 51 Peg was one of them because it was bright. And very rapidly, 51 Peg had a very weird behavior.
On one side, we were absolutely sure of the quality of our measurement. All the signal was in favor of a planet, but it's evident it was a so unusual planet.
And I really thought at that time, oh, there is something really bad in the software on the instruments, and I better to figure out because otherwise my PhD would be compromised.
Over the next several months, the two astronomers checked and rechecked their data. The problem was no one could imagine a giant planet with such a short orbit.
So we came back in July, this time together with Michel, very excited. I said, okay, let's see whether the conclusion that we had with the first bunch of data we had still holds.
The real moment where we had the confirmation of the reality of 51 Peg was really a planet was in July '95.
First data, just on it, we say, okay, just luck. second data, still on the curve. We say, okay, well, 2 is far, but still 2 is not enough. The third one was still on it, following a track. I mean, and then we say, well, let's just wait the fourth to be really, really sure, because it was so embarrassing conclusion, that planet, that we really want to make sure that was real.
We got the good period, the good amplitude, and so on. So at the time was really the time for the celebration. Before we were not sure that it was a planet.
I mean, there is a real planet. Believe it or not, there is no theory to predict that planet, but there is a planet there.
Following days of rumors circling the globe, at a conference in Florence, Italy, the news unofficially leaked. A Jupiter-sized planet had been discovered. This massive planet was making a complete orbit of its star in only 4 days. How could that be?
Suddenly there's this 51 Peg, which is a Jupiter-sized planet, but in a 4-day orbit. And people knew that was impossible. If Jupiter-like planets orbit at like Jupiter and Saturn orbital distances.
Back in San Francisco, Marcy and Butler, by mere coincidence, had 4 consecutive days of reserved telescope time at the Lick Observatory, the exact amount of time needed to confirm or debunk the claim.
We hit the star very hard for those 4 nights. We reduced the data as quickly as we can. We were blown away. We saw exactly the signal that Mayor and Collot had announced.
Confirming my data, to me, was just the best gift I could have had, because I said, oh, fine, so all the work I did is right.
Here in San Francisco, the discovery was dramatically verified just this past weekend.
October 19th, 1995.
What may be the discovery of new planets outside our solar system has created enormous excitement among astronomers.
The confirmation was made before the official announcement of the discovery itself.
It went completely out of control.
Everybody was discussing of this new object, except us.
By tradition, scientists have their discoveries peer-reviewed by other scientists for accuracy.
I was one of the referees on the paper. There were 3 referees, and normally I think they only do 2, but this was so big that the Nature editor, Leslie Sage, was being very careful.
Because of the situations, Nature was very strict. They say, well, look, guys, if you talk to people, then we're not going to publish your paper.
So it's only after 1 month or something like this that I receive a message from Nature that, okay, no, you are relaxed from the embargo.
Because the discovery was just too big, just far too big to follow the usual scheme that is required for a scientific paper. As soon as you start talking about that, I mean, everybody wanted to know about this.
51 Peg B is a real planet, no question about that.
As soon as we detected 51 Peg, he had on his data plenty of something like that. You just need to look at it.
At this point, we hadn't analyzed all our data. We had 2 computers, and it would have literally have taken us 5 or 6 years to get through all of the data. So literally about a half a dozen different groups said, you know, we've just received these new computers, and we're not going to use them for the next several months. You want to dump your jobs on it.
Within 2 months, 2 other Jupiters circling around their stars were found by Marcy and Butler, and the floodgates of planet hunting were now wide open.
You know, from no planets at all to the point where we're discovering a new planet every month or even sometimes every week. And almost all of the planetary systems that we found were very different from the solar system, weren't even similar in the least bit.
I remember asking at a meeting, you know, how long do you think this will go on? And I think Michel Mayor said, maybe, you know, another 5 or 10 years, and then the game is over. Fortunately, the game just got a lot more exciting.
After getting my PhD, I became aware of this fellow at NASA Ames Research Center, Bill Barucki.
I would see him at all these meetings. They were very small meetings back in the day. And like he'd literally be by himself out having dinner, so we would join him and chat about things, and he was very persistent.
Bill walked around the halls, and whenever the Ames managers saw him coming, they turned and walked the other way.
Bill Barucki wrote a paper in the 1980s that described the transit method. When that planet passes in front of the starlight drops by a tiny, tiny amount. And by measuring the brightness of the star, minute by minute, we can detect planets going in front of the star, and we call that the transit method. And detectors that could measure that precise drop in brightness didn't exist yet.
To be successful, all one needed to do was build a photometer 1,000 times better than anyone ever built one. But I'd worked on the Apollo program, I'd worked on other programs, so that's not really that scary. You just need to get down to brass tacks and find out what's required and build it. There just is no way of finding small planets in orbits like that of the Earth unless you go into space. You must go into space.
He kept getting shot down by the review panels for various reasons, and each time he'd fix the reason and go back a second time, and they basically said it's not going to work. Well, Bill Barucki didn't bother reading that report, or at least did not take it to heart. He kept on his crusade to show that transit detection should work.
He was able to demonstrate in the lab that he could measure the precision required to find Earth-sized planets orbiting sun-like stars.
Some people call it stubbornness, but the point is I knew it would work.
So he proposed and reproposed, and eventually he conceived of a Discovery-class mission that was later called Kepler.
It was 25 years between the date of publication and the date that Kepler actually launched.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler just delivered so much tremendously new things we never even conceived of. And the things that were on our wish list, Kepler found for us.
This data was being displayed for the first time on the computer monitors. And there was the transit of that Jupiter-sized planet, and the data was like beads on a string.
Kepler has transformed our understanding of exoplanets. What Kepler was designed to do specifically was to go after terrestrial or rocky planets that are in closer orbits to stars. We now know from the Kepler data that planets like the Earth are in fact common in the galaxy, and that's something we fundamentally didn't know before Kepler.
The first exoplanet was already diverse, and Kepler continued to find more and more planets that didn't fit the norm, both in size, in composition, in distance from their stars. So when you think about how many stars there are in our galaxy, there are a few hundred billion, and if each one has one or maybe more, we're looking at a few 100 billion planets.
To accomplish something great, you have to have persistence.
To succeed in exoplanets, we have to be very ambitious and very bold.
Kepler's impact was extreme, certainly more than I'd ever imagined. It's basically opened up an entire new era of astronomy.
Now that we know that the galaxy is teeming with planets, we are ready to go to the next chapter of planetary exploration.
I truly believe that the 2020s are shaping up to be a golden age for observational astrophysics. We have these amazing telescopes like TESS, the Transiting Exoplanet Survey Satellite. We have WFIRST, which is this Hubble-sized telescope that can see 100 times as much of the sky in each image. We have the James Webb Space Telescope, which is, the largest and most powerful telescope we've ever built. The reason that we can even dream about that and create something like that is because of the success of Spitzer and Hubble and the previous great observatories.
I'm looking forward to space-based missions where they're going to have coronagraph technology and maybe even star shield technology in order to image exoplanets by blocking out the light from stars.
And we have the next generation large 30-meter class telescopes on the ground, which are going to be coming online in the 2020s. But the question that has me most excited about the future of astronomy is to answer the question, are we alone in the universe?
Finding evidence of life on an exoplanet, finding an indication of a living world is within our reach.
What is life? Life is a process to transfer information from one generation to another.
Everybody is interested in the search for planets, the search for places that remind us of home.
We're looking for some hint of our origins, where we came from, and exoplanets may very well provide that context.
There may be more habitable real estate out there beyond our solar system than we once thought.
I think we're naturally curious to find out if there are other conditions in the universe that might be similar to our own. And finding exoplanets around other stars is the first important clue.
The search for planets is a search for life. And even though we didn't really say that out loud, that was always in the back of our minds.